Hey everyone. So today I want to talk about system design, but not the kind you usually see in interview prep videos. We're not going to start by drawing boxes for load balancers or databases and just connecting them with arrows like they're Lego blocks. That's kind of the surface level way of doing things. Instead, I want to go back to basics. I want to talk about the physics of software. You see, I remember this one time. I was working on a high-throughput ingestion service. We had this best practice architecture. We had a distributed cache. We had a microservices layer, the whole deal. But under heavy load, the system started crawling. Latency was spiking to 500 milliseconds. The junior engineers were saying, "We need more nodes. We need to shard the database." But when we actually looked at the telemetry, we realized something embarrassing. Our fast distributed cache was actually the bottleneck. Why? Because the developers hadn't accounted for the network round-trip time. They were making 50 small network calls to the cache for every single user request. In their heads, cache equals fast. But in the world of physics, network equals slow. They were fighting against the speed of light, and the speed of light was winning. To be a senior engineer, especially at a place like Google or Netflix, you have to stop thinking in terms of tools and start thinking in terms of latencies, throughput, and physical constraints. If you don't understand the hardware underneath your code, your abstractions will eventually leak and your system will fail. So let's look at the numbers. Let's look at the latency numbers every programmer should know. This is our periodic table. This is where system design actually begins. Okay, so let's get into the mental model. Imagine your CPU is the brain. It's incredibly fast. It's ticking at maybe 3 gigahertz. That means every cycle, every heartbeat of the processor takes about 0.3 nanoseconds. Now, a nanosecond is a hard unit to wrap our human brains around. So let's scale it up. Let's imagine that one CPU cycle is equivalent to 1 second of human time. If one CPU cycle is 1 second, then fetching data from the L1 cache, the memory sitting right on the chip, takes about 4 seconds. That's like reaching for a notebook on your desk. Pretty quick, right? But what if the data isn't in the L1 cache? What if we have to go to main memory, RAM? In our scaled-up world, a RAM fetch takes about 100 seconds. Now you're not just reaching for a notebook, you're standing up, walking to a bookshelf at the back of the room, finding the book, and sitting back down. You can feel the delay, but it's still manageable. But here is where things get problematic. What happens when we have to read from a solid-state drive, an SSD? In our 1 cycle equals 1 second world, reading from an SSD takes about 2 to 6 days. Think about that. Your CPU, your brain, is waiting for days just to get a single piece of information from the disk. This is why we obsess over caching. This is why we try to keep everything in RAM. And it gets worse. What if we have to send a packet from California to a data center in the Netherlands and back? That's a round-trip time of maybe 150 milliseconds. In our world, that is 15 years. So when you write code that says await cache.get of key inside a loop that runs 100 times, you aren't just fetching data, you are asking your CPU to wait for decades of its life. This is the first principle. Data has distance. As a system designer, your job is to minimize the distance of data. If you are building a high-performance system, you cannot treat a local variable the same way you treat a database record or a network call. They are orders of magnitude apart in the physical world.
Now let's talk about mechanical sympathy. This is a term coined by Jackie Stewart, a racing driver, who said that to be a great driver, you don't need to be an engineer, but you must have a sympathy for how the machine works. In system design, this means understanding how bits are actually moving on the hardware. Let's look at sequential versus random I/O. This is one of the most important first principles. A hard disk drive, the old spitting platters, is actually decent at reading data if it's all in one long line, sequential. But if the data is scattered everywhere, random, the head of the disk has to physically move. It's like trying to play a vinyl record but skipping to a different song every 2 seconds. It's slow. Even with SSDs, which don't have moving parts, we still have this constraint. Reading a large block of data sequentially is significantly faster than jumping around to random memory addresses. Why does this matter for system design? It tells us why databases are designed the way they are. This is why LSM-Trees, used in NoSQL like Cassandra or RocksDB, are so fast for writes, because they turn random writes into sequential writes. They just append data to the end of a file. It's mechanically sympathetic. If you understand this, you don't just choose NoSQL because it's trendy. You choose it because you know your hardware loves sequential writes and you're willing to trade off read complexity for write throughput. See? We're building from the physics up. We're not just talking about Cassandra. We're talking about the physical reality of how a voltage change on a flash chip or a magnetic flip on a platter dictates the architecture of a global scale application.
So we've talked about the distance of data, but distance is only half the story. The other half is what I like to call the pipe problem. In formal terms, this is the distinction between latency and bandwidth. People often confuse these two, but they are governed by very different physical realities. Think of it like a water pipe. Latency is how long it takes for a single drop of water to travel from one end of the pipe to the other. That's governed by the speed of light in fiber optics, or the speed of electrons in copper. You can't really make that faster without moving the servers closer together. Physics says no. Bandwidth, on the other hand, is the diameter of the pipe. It's how much water can flow through at once. You can always buy a bigger pipe. You can add more fiber optic cables. You can add more RAM channels. Actually, there's a classic thought experiment in computer science. Never underestimate the bandwidth of a station wagon full of tapes hurtling down the highway. If you fill a Boeing 747 with 15 petabytes of hard drives and fly it from New York to London, the latency is terrible. It's 8 hours. That's a huge delay. But the bandwidth? It's massive. If you calculate the bits per second, that airplane is faster than any internet connection on Earth. Why does this matter for your system design? Because as a senior engineer, you have to decide, are you latency bound or bandwidth bound? If you're building a high-frequency trading platform, you are fighting for latency. Every microsecond is a loss. You need the shortest path. But if you're building a video streaming service like YouTube or Netflix, you don't care if the first bit takes 200 milliseconds to arrive, as long as the bandwidth is wide enough to keep the data flowing once it starts. When you see a system choking, the first thing you should ask is the pipe too long, latency, or is the pipe too narrow, bandwidth? If you try to solve a latency problem by buying more bandwidth, you're just wasting money. You're building a wider pipe, but the water still takes 8 hours to get across the ocean. This is where first principles thinking saves you from expensive architectural mistakes.
Okay, let's step up the abstraction just one level. We've looked at the hardware, now let's look at the math of how requests flow through that hardware. This is where we meet Little's Law. It's a deceptively simple formula from queuing theory, but it governs everything from a Starbucks line to a distributed microservice. The law is L equals lambda W. L is the number of requests in your system. Lambda is the arrival rate, how many users are hitting your site per second, and W is the average time it takes to process one request, latency. It's a beautiful equation because it's a law of physics for software. It tells us that if your service takes 1 second to process a request and you get 100 requests per second, you will always have 100 requests sitting in your system at any given time. If your latency, W, increases, maybe because the database is slow, your L, the number of in-flight requests, must increase. But here's the kicker. Your servers have a physical limit for L. Your RAM can only hold so many open connections. Your CPU can only track so many threads. Once you hit that physical limit of L, the system doesn't just stay full, it starts to buffer. It creates a queue. And as the queue grows, the wait time for the next user increases. This is a positive feedback loop of death. This is why systems don't just slow down, they often fall over suddenly. As a senior engineer, you don't just monitor CPU usage, you monitor the relationship between lambda and W. If you see your latency, W, creeping up while your arrival rate, lambda, stays the same, you know mathematically that your system is about to hit a wall. You can't engineer your way out of Little's law. You can only change the variables. You either decrease the work, W, by optimizing code, or you increase the system's capacity to hold L by adding more hardware. This is bottom-up thinking. It's not a DevOps problem. It's a math problem.
The final first principle I want to touch on today is economics. I know, economics doesn't sound like physics, but in the cloud, they are the same thing. In the old days, you bought a server. It was a capital expense. Today, we rent slices of hardware, but we aren't just renting compute. We are renting time and physics. Every time you choose a managed service or a specific instance type on AWS or GCP, you are making a physical trade-off. Let's look at the cost of storage. Storing 1 gigabyte in RAM is roughly 100 times more expensive than storing it on an SSD, and storing it on an SSD is 10 times more expensive than cold storage, or S3. If you design a system that keeps all user profiles in a distributed Redis cache just in case, you are essentially choosing a very expensive physical medium for data that might not need it. A senior staff engineer's job is to align the value of the data with the cost of the physics required to store it. If the data is hot, meaning it's accessed 1,000 times a second, it belongs in the L1, L2 RAM layers. It's worth the rent. If the data is cold, like a receipt from 3 years ago, keeping it in a high-bandwidth, low-latency medium is an engineering failure. It's like renting a penthouse apartment in Manhattan just to store your old cardboard boxes. When you sit down to design a system, ask yourself, what is the price per bit of this architecture? If you don't know the answer, you haven't finished the design, because at FAANG Scale, a 1% efficiency gain in how you use your RAM isn't just clean code, it's $10 million a year saved in the data center. That is the level of impact we are looking for. So let's wrap this up. We started by looking at the nanoseconds of a CPU cycle, and we ended by looking at the millions of dollars in a data center budget. The first principles approach to system design is about seeing the thread that connects those two things. You don't start with a microservice. You start with the latency. How far does the data have to travel? The throughput. How wide is the pipe? The state. Is the work sequential or random? The math. What does Little's law say about my capacity? The cost. Is the physical medium worth the business value? If you can answer those 5 questions, the boxes and arrows of your architecture will practically draw themselves. You won't be guessing, you'll be calculating. In the next video, we're going to take these physical constraints and apply them to scalability. We'll see what happens when you take these principles and multiply them by 100 million users. It gets messy, but the physics stays the same. Here's your challenge for the comments. Think about a system you're working on right now. Pick one network call it makes. Calculate the human time equivalent of that call using our 1 CPU cycle equals 1 second scale. Is your CPU waiting for a day, a month, a decade? Post your results below and tell me, how would you redesign that system if you were forced to keep that CPU brain busy? I'll be down there reading and responding. Let's build something efficient. I'll see you in the next one.